Hey there, AP chemistry fans. Today we're going to be doing a fast and furious introduction to acids and bases. So get your pens ready and let's get started. First off, here's a list of vocabulary that will be covered in this presentation. If you want to write these down, you might want to go ahead and pause right now, and then you know what to look for later in the presentation. So, first of all, what are acids and bases? Well, originally, acids and bases were categories of chemicals that were just classified based on their chemical and physical properties. For instance, acids had a sour taste, reacted with active metals to produce hydrogen gas. And what I mean by active metal is any metal on the activity series higher than hydrogen. It turned litmus red. Litmus is a acid-base indicator that changes in response to the presence of an acid or a base. And when it's in the presence of an acid, it turns red. Acids conduct electricity and they neutralize bases. So if a substance fit these categories, then we called it an acid. Bases, on the other hand, had a bitter taste, a slippery feel, dissolved fats and oils, turned litmus blue, conduct electricity, and neutralize acids. So if a chemical fit these categories, then it was called a base. Later definitions were developed in order to define what an acid and a base were and why they had these characteristics. And so the two that we're going to be looking at are the Arrhenius definition and the Bronsted-Lowry definition. So first, let's take a look at the Arrhenius definition. The Arrhenius definition is based on how acids and bases behave when they're placed in water. Acids, when they're placed in water, produce hydronium ions. And hydronium is a polyatomic ion, H3O positive, where a water molecule has gained a hydrogen positive ion. Note that a lot of times H3O positive is written just as H positive, since that's what is attaching to the water molecule. So you'll see both of those, and they're interchangeable. However, H3O positive is preferable, especially on the AP test. Bases, on the other hand, produce hydroxide ions when placed in water. So if you put a base in water, then the concentration of hydroxide will increase in the water, which is OH negative. So some examples of acids in water: if you take HCl and place it in water, the water takes that hydrogen ion off of the HCl, leaves behind the chloride ion, and makes H3O positive. And so you see that formation of H3O positive, which is why it is an acid according to the Arrhenius definition. This is called ionization. Notice that the chloride and the hydrogen get separated from one another. Even though it's a molecular compound, the hydrogen becomes positive and the chloride becomes negative. So a lot of times, instead of writing the reaction with water, we'll just show the splitting of the hydrogen and chloride ions in that ionization process. And these two are exactly the same representation, or two representations of the exact same process. Here's another acid when it's in water. This is acetic acid, the acid that's present in vinegar. And you'll see that hydrogen in front bonded to the acetate ion. The water steals that hydrogen ion and becomes H3O positive, which is the hydronium ion. And then the acetate ion is broken off of that hydrogen ion. And so again, you see this ionization and the formation of hydronium ions when placed in water. Examples of bases in water. There's two different ways that bases make hydroxide when they're placed in water. One is if an ionic compound is placed in water that has hydroxide, the positive ion and the hydroxide dissociate from one another, just like a normal dissociation of an ionic compound, and you make a positive cation and then the negative hydroxide ions. So the formation of hydroxide in water makes this a base. Another way bases can form hydroxide in water is by donating or by having water give a hydrogen ion to the base. So NH3 is a weak base, it's ammonia, and it can accept a hydrogen ion to make NH4 positive. When it does that, the water now has one less hydrogen ion and leaves behind hydroxide. This is called hydrolysis when it reacts with the water molecule itself. You're going to learn more about how to recognize acids and bases as we go through this unit. Right now, I don't expect you to know that NH3 would steal that hydrogen ion from water, but over time you will. The Bronsted-Lowry definition of acids and bases is based on how acids and bases react with one another. When you put an acid and a base together, acids will donate a proton. And just so you know, a proton is a hydrogen ion. Remember, hydrogen has one proton and one electron. So if a hydrogen atom loses an electron, it becomes a hydrogen ion, and all that's left is a proton. So you'll see the word proton and hydrogen ion and H positive all interchangeable as we go through the acid-base unit. So acids are proton donors. They give away a hydrogen ion. Bases are proton acceptors. So they accept a hydrogen ion. So let's see a couple of examples of this. Here is hydrochloric acid, HCl, reacting with ammonia. HCl is going to donate a hydrogen ion to the NH3. We saw that NH3 could accept hydrogen ions earlier. And so the NH3 now becomes NH4 positive because it gained that positive hydrogen. And chloride is left behind as a negative ion. Now we have labels for all of the particles that are present in this situation. HCl is an acid and NH3 is a base, of course. But then after the acid loses its hydrogen ion, it becomes a conjugate base. And the base, once it gains the hydrogen ion, becomes a conjugate acid. Why did they switch names as far as base and acid? Well, now the conjugate base doesn't have a hydrogen to give away, but it could accept a hydrogen, and that's why it's now called a base. The conjugate acid now has an extra hydrogen ion, and so it could give away a hydrogen ion, and that's why it's now called an acid. So the acid and conjugate base are called a conjugate pair. The acid became the conjugate base after it lost the hydrogen ion. And then the base gained a hydrogen ion, and now it is a conjugate pair. So in this acid-base reaction, we have two conjugate pairs, the acid and its conjugate base, and the base and its conjugate acid. Conjugate pairs are important to recognize in acid-base reactions, and we'll see more of this later on. Here's another example. The OCl, the hypochlorite ion with a negative charge, reacting with hydrofluoric acid, HF. So HF is going to give a hydrogen ion to OCl negative. Since OCl negative is negative, it's capable of gaining a positive ion. So OCl negative with the hydrogen is now HOCl. And then what's left of the acid is the fluoride ion. So OCl minus becomes the conjugate acid because it gained that hydrogen. The base becomes the conjugate acid. And then the acid, HF, becomes the conjugate base. So what are the conjugate pairs? OCl minus and HOCl are a conjugate pair, and HF and F minus are a conjugate pair. So let's talk a little bit about water. Since water gets involved in all these acid-base reactions, water actually behaves like an acid or a base depending on what substance it's with. For this reason, we say it's amphiteric or amphiteric. Not amphiteric, sorry, amphiprotic. Amphi meaning both and protic meaning proton. So water can give away hydrogen ions and water can gain hydrogen ions. So we say it's amphiprotic, both protons. So here's an example. F minus is capable of gaining a hydrogen ion. And so in this case, water is going to donate a hydrogen ion to the fluoride ion, and it becomes HF on the product side. After water gives away that hydrogen ion, it becomes OH negative. And so in this particular case, water is behaving like an acid, and fluoride is behaving like a base. The acid conjugate base pair is water as an acid and OH as a conjugate base. That's the acid conjugate base pair. And then the base gained a hydrogen ion, so F minus is a conjugate pair with the conjugate acid, HF. Here's another example. Can you identify the acid, base, conjugate acid, and conjugate base? Here they are. The acid always gives away a hydrogen, the base always accepts a hydrogen. So in this case, water is behaving like a base because it steals that hydrogen from the acid. So when water is in the presence of an acid, it'll behave like a base. And when water is in the presence of a base, it'll behave like an acid. And then the conjugate pairs are the acid and conjugate base, and the base and the conjugate acid. So since water can behave like both an acid and a base, When it's by itself, it behaves like both. It auto-ionizes. It ionizes itself to a very small extent. So one hydrogen molecule will donate a hydrogen to another water molecule. And I think I said that right. One water molecule will donate a hydrogen to another water molecule. And when that happens, the one that donated the hydrogen becomes OH minus. The one that gains the hydrogen ion becomes H3O positive. And so you'll see that we produce hydroxide and hydronium in water. And so water behaves like an acid and a base. Now, this is an equilibrium because this only happens to a small extent. And since it's an equilibrium, there's a K value. We call this Kw. And when water is by itself, Kw equals the concentration of hydronium times the concentration of hydroxide, which is equal to 1 times 10 to the negative 14 at 25 degrees Celsius. Now, please note, this value will change if the temperature changes, like all equilibrium constants. So at 25 degrees Celsius, which is a very common temperature, this is the value of K. Kw is true no matter what is in it. If we put an acid in water, Kw is still 1 times 10 to the negative 14 at 25 degrees Celsius. If we put a base in water, Kw is still 1.0 times 10 to the negative 14 at 25 degrees Celsius. It's just that the concentrations of hydronium and hydroxide go up or go down depending on what's present. But in water, the concentrations are equal. So how can we measure the concentrations of hydronium and hydroxide? Well, pH is a measurement of the hydronium concentration in solution. The typical range of hydronium in any solution is huge, 1 times 10 to the negative 14th molar, all the way to 1 times 10 to the 0 molar. This is the typical range, and you can go a little outside of this, but this is the typical range of the hydronium concentration in any solution, whether it's neutral, acidic, or basic. So when the hydronium concentration is high, like 1 times 10 to the 0, then that is more acidic. When the concentration is really, really low for hydronium, like 1 times 10 to the negative 14, then that's more alkaline. And alkaline is simply a word for basic. And so the range goes from 1 times 10 to the 0, acidic, to 1 times 10 to the negative 14, very, very basic, with 1 times 10 to the negative 7 right in the middle, which is neutral. So you might recognize something about those exponents on the hydronium concentrations. You might notice that they are the pH scale. The pH scale is simply those positive values of those exponents on the concentrations of hydronium. So 0 to 14 is the range for the pH scale, with 7 right in the middle, which is more neutral. So as you go away from 7 down, it becomes more acidic, and as you go away from 7 up, it becomes more alkaline or more basic. One thing I just noticed on this is that I have the positive sign outside the brackets here. Please note that that positive sign should be inside the brackets for the H3O positive. So that is a typo and probably will be on future slides too. So because the range of hydronium is so many magnitudes of 10, then we've developed the pH scale, which tells us about the exponent of the concentration of the hydronium concentration. So it's a logarithmic scale, and the way we calculate pH is take the negative log of the hydronium concentration. So you want to write that formula down because you'll be using it quite a bit. So let's do some practice with it. Let's say that the pH of a solution has let's say a solution has a hydronium concentration of 0.05 molar, and we want to figure out what the pH is. So we're going to plug that concentration into the pH equation. pH equals the negative log of the hydronium concentration. And when you do that, taking the negative log of 0.05, you get 1.301. One thing to note about, never mind, I'm going to leave it there. 1.301 is the pH. Let's do the inverse. What if I give you the pH, 9.42, and we want to solve for the hydronium concentration? So if we do this calculation, we plug 9.42 in for the pH. We need to solve for the hydronium concentration, so we need to rearrange this equation. And so the concentration of hydronium equals 10 to the negative 9.42, because the opposite of log is antilog, which is 10 to the exponent. And when you do that, you get an answer of 3.8 times 10 to the negative 10. And there should be a molar on the end of that because it's a concentration. So 3.8 times 10 to the negative 10 molar. What about pOH? What if we want to talk about the hydroxide concentration? Well, there's another scale for that, the pOH scale. And pOH is just like pH, except instead of hydronium, it's a measure of the hydroxide concentration. So if you recall, we saw that hydronium times hydroxide always equals 1.0 times 10 to the negative 14 at 25 degrees Celsius, which means that hydronium and hydroxide are inversely related. So we saw earlier that the hydronium concentration uh, has a range of 1 times 10 to the negative 1 times 10 to the 0 for more acidic solutions and 1 times 10 to the negative 14 for more basic solutions. The hydroxide concentration is exactly the opposite. 1 times 10 to the negative 14 for more acidic solutions to 1 times 10 to the 0 for more alkaline solutions. So the pH goes from 0 to 14 from acid to base, and the pOH scale is exactly the opposite, 14 to 0 for acid to basic. So the equation for the pOH scale is just like the pH equation, but it's going to be the negative log of the hydroxide concentration. So let's do a couple of practice with this. What is the pOH of a solution with a hydroxide concentration of 5.3 times 10 to the negative 4 molar? So to figure out the pOH, we simply plug in the hydroxide concentration, the negative log of the hydroxide concentration, and when you do that on your calculator, you should get 3.28. What if we need to do the opposite? What if I give you the pOH and you need to solve for the hydroxide concentration? Well, just like with pH, we plug in the pOH into the equation. We rearrange the equation by dividing by -1 and then taking the antilog. So the antilog of negative 6.49. And so we get a hydroxide concentration of 3.2 times 10 to the negative 7. And again, there should be a molarity on the end of that because this is concentration. So there should be a capital M at the end here for molarity. So pH and pOH have a relationship based on the hydroxide and hydronium concentration. And you might notice that the pH plus the pOH always equals 14. And again, this is at 25 degrees Celsius. If the temperature changes, then the pH plus the pOH will not add up to 14. It'll be slightly different than that. So at 25 degrees Celsius, the pH and the pOH add up to 14. So just a couple of easy calculations here. If the pH is 4.28, what's the pOH? Well, we just take 14 and subtract the pH. That will give us the pOH, 9.72. What about if we have a hydroxide concentration of 6.13 times 10 to negative 3 molar and we want to solve for the pH? Well, the first thing you'll want to do is, this is the hydroxide concentration, and for pH we need the hydronium concentration. So the first thing we need to do is let's solve for the pOH of this solution, because we know that pH plus pOH equal 14. So if we know the pOH, we can solve for the pH. So pOH is negative log of the hydroxide concentration. That'll give us a pOH of 2.2125. If we plug that into the pH plus pOH equals 14 equation, then we get a pH of 11.797. So our last concept in this slide presentation is strong versus weak acids and bases. So strong and weak have very definite meanings when it comes to acids and bases. And this word strong means that your acid or your base ionizes or dissociates 100%. In other words, it doesn't set up an equilibrium. Every single molecule of reactant becomes product. So, for instance, hydrochloric acid is a strong acid. It does not set up an equilibrium where hydrogen and chloride separate, but then hydrogen ions and chloride ions recombine to make HCl. They stay completely separated. So strong acids and strong bases completely break apart. Sodium hydroxide is also a strong substance. It's a strong base. The sodium ions and the hydroxide ions 100% dissociate into sodium ions and hydroxide ions. And so because of this, we call it a strong base. So how do you know what the strong acids and strong bases are? Sadly, you have to memorize them. The strong acids um, there's 6 strong acids that you'll need to know, and there are 7 strong bases that you'll need to know. And if they aren't on this list, then you can assume that they are weak acids and bases. So the strong acids are HCl, HBr, and HI. Those are the halogens bonded to hydrogen. Notice that fluorine is not in there. HF is a weak acid. HNO3, H2SO4, and HClO4 are also strong acids. Please notice that H2SO4 is a diprotic acid. Diprotic means it has 2 hydrogen ions that can come off of it. And so if it has 2 hydrogens, we call it a diprotic acid. All the others in this list are what are called monoprotic acids. They give away 1 hydrogen only. The strong bases are group 1 metals bonded to hydroxide. So lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide. Then also we have 2 group 2 hydroxides, barium hydroxide and strontium hydroxide. Every once in a while you might see calcium hydroxide listed in this list, but it is moderately strong. It is not completely strong in that it doesn't completely dissociate into calcium hydroxide. So like I said, you do need to memorize these. And just a reminder, an acid that can give away 1 proton is called a monoprotic acid. If they give away 2 protons, it's called a diprotic acid. Some acids can give away 3 protons, and we call those triprotic. And anything that can give away more than 1 is called polyprotic. So diprotic and triprotic are both polyprotic. So those are just vocabulary terms to know about how many hydrogens an acid can give away. Strong acids and strong bases ionize or dissociate 100%. The concentration of the acid or base is the concentration of hydronium or hydroxide, respectively. In other words, if you have a 1.5 molar HCl solution, remember that HCl breaks apart 100%. So you actually have no HCl molecules in the solution. They have broken up into hydrogen ions, which is the hydronium ion, and chloride ions. And so this rise table shows what I mean. If we start off initially with 1.5 molar HCl, all of that HCl breaks apart and dissociates into H positive and Cl minus. And therefore, you have no HCl actually present, but you do have 1.5 molar H positive, which is hydronium, and 1.5 molar Cl minus. And therefore, if you know the concentration of a strong acid, you know the concentration of the hydronium in that strong acid. Same is true for a strong base. If, for instance, we have a 0.5 molar NaOH solution, then that NaOH 100% dissociates. The Na ions and the hydroxide ions break apart 100%. So it's actually 0.5 molar hydroxide, not 0.5 molar sodium hydroxide. Even though we label it 0.5 molar sodium hydroxide, a chemist knows that that has dissociated and broken into hydroxide ions and is 0.5 molar hydroxide. Again, looking at this Rice table, if initially it's sodium hydroxide 0.5 molar, all of that sodium hydroxide breaks apart. And so we gain 0.5 molar sodium ions and 0.5 molar hydroxide ions. And so the hydroxide ion concentration is 0.5 molar. So if we know the concentration of the strong acid or strong base, then we know the concentration of hydronium or hydroxide. Let's just look at a quick example of this. What is the pH of a 0.0042 molar HBr solution? So since HBr is a strong acid, it's in the strong acid list, then we actually don't have 0.0042 molar HBr. We actually have 0.0042 molar H and 0.0042 molar Br. So to calculate the pH, we simply plug in that concentration, since that's the concentration of hydronium or hydrogen ions. So we plug that into the pH equation and we get a pH of 2.38. We can also do this with bases. Let's do another problem with a base. So if we have a 0.55 molar lithium hydroxide solution, what is the pH of this? Well, again, this is the concentration of the OH ions. Even though we're labeling it the concentration of lithium hydroxide doesn't really exist because it splits apart. It dissociates into its ions. So this is the concentration of the hydroxide ions. So first we need to find the POH, And once we know the pOH, then we can plug that into the pH plus pOH equals 14 equation. So pH equals 14 minus 0.26, which is the pOH, and we get a pH of 13.740. So that's it for now. I know that was really fast, but we're going to do practice in class and see applications of this, and you will get it under your belt as we go through other material. So good luck, and if you have any questions, of course, as always, please ask.